So we continue with feature extraction, feature generation from relational databases. And now we're going to look at the features that are defined using aggregate queries. Okay, so we call them join aggregate features. Okay, and the question you need to ask is the following. We've been looking at tuples that reference other tuples. Target the tuple um, with another referenced tuple, and we said, okay, you can use attributes of the referenced tuple as your features, and that's fine. But what if the other tuple references the target tuple? Okay, you have a reference in the opposite direction. Well, the problem is that you can have many such tuples referencing T using the same foreign key constraint. Okay, and you cannot make a feature out of these. First, there can be, an unbounded number of such tuples, and then it's different. It's a different number for every target tuple. You need to somehow deal with all of these tuples. And we need to transform them into a single scalar, a single element that will be our feature. Okay? So this is basically what aggregate functions do and the operation of aggregate queries. And we'll revisit what this means. But here's an example to have in mind. So our target table or target rows are the student rows. And let's look at student 89. If we look at the took tuples that reference the student, there are these two, okay? And we can say, okay, these are two courses that the student takes, and we can use the grades. For example, take the average grade. So we take all of these grades, you aggregate them through the average function, and that gives us a number. Okay, so that's an example. Okay, so let's make it more general. So an aggregate function takes a set of values or a bag of values because we allow duplicates and outputs a single element, a single scalar. And there are common basic aggregate functions in SQL: min, max, sum, average, median, count, count distinct. And they assume a single column, except for count and count distinct. They can also operate on a full table. Okay, some of them assume a numeric domain, and they can be also undefined. For example, if you have an empty set of or an empty bag, average of the empty bag is not well defined, so the result is null. Okay, min max can operate not just on numeric domains, but also on strings, for example, because there's a lexicographic order there. Okay, and that's also a feature. So there's a standard list of SQL aggregate functions, and every database brand or vendor also publishes its own supported list of aggregate queries. For example, this table is part of the MySQL documentation. And you can see there are aggregate functions that operate on bits and ones that do statistics and many others. All right, so aggregate queries. How does an aggregate query look like? The structure looks like that. Select G, comma, aggregation over attribute A from, well, here you have some join expression that might involve several tables, but includes the attributes G and A. And this is followed by group by G. Okay, so what is the meaning? So G here serves as the grouping attribute. Okay, and in our case, G is going to be the ID element or the ID attribute of the target table, T.ID. So we're going to group elements by the target instance. Okay? And then the semantics is very simple. You apply the join, you get one big table that involves the attribute or uses the attributes G and A. You group together all of the tuples that have the same G value. And for each group, you take the A column. That gives you a bag. You apply your aggregate, and then you get your result. So result is basically the group element, the group identifier, comma, the aggregated value, a pair. Again, that's how we'll get our features. So for example, if you apply select of a aggregation over A, ag for example, sum, average, then the semantics is, well, take this column, apply the aggregate, and you get one value. You can also look at this query, select G, comma, ag A, group by G, and this will mean take the G column, group the tuples by the G value. So we have here three groups, one for A, one for B, one for C. In each of them, take the A column and apply your aggregate function. So that gives you three pairs, okay, the three tuples. Okay, so going back to our example, we use a backward reference SB contained in the key of T, okay? And then what do we need in order to produce a feature? So we need to choose an aggregate function or an aggregation function, ag. We choose an aggregated attribute of S. Okay, this is the attribute that we're going to process. And then for each tuple T in our T database, this is a target instance basically, we aggregate the values of S for the attribute A of all the tuples S in the S table. D is our database. All of the tuples S that reference T. So it looks like that. Select T.id, comma, aggregation over S.A. We call it as usual AI. From what? Well, T join S based on the foreign key. Group by TID. We group by the target instance. Okay. Now, with this tool, we basically can essentially get the arbitrary information from the database because now we can apply whatever joins we want and then choose whatever attribute that we want and we can apply an attribute and that's all. So you can think of uh, uh, arbitrary queries of the form TID, comma, select TID, comma, aggregate over some relation, group by TID, and then what you have here in the from is T join, and then a sequence of tables, S1, S2, all the way to the table, the relation from which you use the aggregated attribute. Okay, here's an example. So we have our student, Anna, 89. We look at the tuples that reference Anna. These are courses that she took. And from each course, we can go to the course relation and use the credit attribute. So, for example, we can have a feature for Anna saying what is the number of credits that she took. Or we can further say, okay, take these courses that she took, now take the students or take the took rows that reference these courses, and then they have their grades, and you can aggregate their grades. For example, take the average of these grades. So the average of the grades of the courses that Anna took, that's another feature. Okay. Now, as a side note, I'll say that understanding the properties of features that involve joins either testing or counting joins is something that is well studied. We did some theoretical work on understanding how these serve as features in machine learning. And you can think of these counts as, say, count the triangles that connect to a node in a graph. And how does it look like? You say, okay, suppose that my graph is represented by this E relation, the edge relation. And then you say, okay, take your target instance and join it with the edge relation. Okay. And that connects to the edge using its source. Then connect again, join again with E, but now call it E2. So the target of E1 is the source of E2. Connect it again with E. Now call it E3. And the target of E2 is equal to the source of E3. And then you close the triangle E dot target is equal to the source of E1. So this basically, and you group by TAT, so you basically count how many triangles are connected to your target instance. And this is basically a special case of extracting graphlet features from a graph. And in the next part, where we're going to talk about graph feature generation on graphs, this is one of the techniques that I'm going to talk about, graphlet features. Okay? So now let us talk about an example of a system that essentially implements this idea or these ideas. So this is the Akora system, okay? And its operation is to construct features automatically from a relational database and then apply some machine learning on top of them, okay? Now, the idea is that they build these joint expressions gradually, and they have a routine saying, okay, given what I have so far in a new relation, is it joinable? Is it joinable on some attribute? Okay, so that's one thing. And then they deploy a collection of aggregate functions. Say, okay, is this aggregate function applicable to this attribute? And then they simply apply. In the end, they get many, many features and then deploy techniques for feature selection. Okay, and we'll talk about it uh, in the end of this part. Okay, but this is their pseudocode, rather simple conceptually. Okay, so there is an initialization. There is this part where they essentially iterate over the relations, every time finding a new relation to join. And then once they have this relation, they look at the different attributes and the target observation. And find an aggregator, an aggregation operator, apply this aggregation and get a feature. And that's that's the whole idea. In the end, they apply some feature selection, select features SF from F, and build their model out of the selected features. That's the Akora system, and they can read the paper. They run experiments there saying how many joins do I need to actually get value from the machine learning algorithm. So you can see they measure the area under the curve and say, okay, in one data set, 2 joins are enough. In other data sets, as you go along with more joins, you get more value, more accuracy, and there is a risk of overfitting naturally. So you can see examples in the paper. They also have some nice figures showing how they iterate, explore the space of expressions, the joins. So you say, okay, I have this paper relation with a paper identifier and a class, and it relates to the author relation, where you basically say which paper was written by which author. So that's one connection that the author can have, and author can join with itself. For example, another paper by the same author. And this paper is also referenced by the citation relation. So there's a paper ID references another paper ID. So that actually two references to paper. So you can use the first PID or the second PID. And this is basically how they continue and extract relations and extract the features and produce their features. Now let's talk in the end about feature selection. So basically feature selection is a task of I have many features and I want to select a small subset of the columns of the features, ones that are good, ones that do the job, and maybe even improve my prediction because now there might be a lower risk of overfitting. And there are several techniques for that, classes, right, of feature selection techniques. There are filter methods where you basically apply some scoring function to each attribute, the attribute, each column, and you basically take the top K. And these can involve information theory, how much information do you have about the um, target element, for example, or some statistical correlation with the training target, and so on. So that's one class of techniques. Another is a wrapper method, where basically you use your training data and your training process to find out the good features. Okay, so you can think of, well, let's start with nothing, and then each time find the next feature that puts me in the best position, that increases my accuracy in the maximum extent. That will be my next feature. And then I'll select the next feature and the next feature again. So that's forward selection. You can go backward and say, let's start with all of the features. And then try eliminating different features and eliminate the ones where I'm losing the least information or actually improving, my accuracy. I can think of exhaustive ways. For example, check every subset of some set. Okay, there are also embedded methods where basically your feature selection is embedded within your machine learning algorithm. Okay, so you uh, basically want to use your regularization, or you usually will use your regularization component. Um, to find your features because regularization typically eliminates redundant features, for example. Okay, or it simplifies your selected model by eliminating features. Okay, now I will say that this is related to dimensionality reduction, but it's not the same as dimensionality reduction because in dimensionality reduction you don't need to use the same features or a subset of the features that you started with. You just need a set of columns, a smaller set of a column of a smaller dimension that essentially preserves the information that you need. So we'll talk about such techniques later in the course. Okay? And that was it about features from databases. Next, we're going to talk about features from graphs.